Let's jump right into this explainer. Today we're asking a really fundamental question about the physical heartbeat of Singapore's power grid. Exactly how far can voltage drift before it becomes a major compliance problem?
Voltage on a real, breathing grid, it always drifts. As massive industrial loads switch on and off, it's constantly fluctuating. But there are strict legal limits keeping things in check. The question isn't whether it drifts. Drift happens. The real question is how far it's allowed to drift under the transmission code before equipment actually starts failing.
And here is the golden rule for steady-state conditions. 400 kV voltage is permitted to vary by only plus or minus 5%. Meanwhile, everything else, your 230 kV, 66 kV, 22 kV, 6.6 kV, and low voltage, they are all held within a slightly wider plus or minus 6% band.
So 400 kV gets the tightest leash. Why? Because it's the absolute backbone of the grid. A 5% swing there represents enormous absolute megawatts. So, as a rule of thumb, default to 6% and then double-check specifically for 400 kV because it is the sole exception.
Let's test this out with a quick scenario. Say you get a voltmeter reading of exactly 424 kilovolts on a 400 kilovolt nominal line. Based on the rules, is that compliant?
No way. Absolutely not. The plus or minus 5% band tops out at exactly 420 kilovolts, so 424 kilovolts is a definitive legal violation.
But keep this vital caveat in mind. These really tight percentages only apply to steady-state limits. Transient events, like a sudden switching surge, they have their own much wider tolerance bands. Okay, so before this, you knew the voltage tiers, and now you know the exact steady-state limits. You can check any reading against its legal band. But magnitude is just one axis of power quality. Next, we need to look at power factor, harmonics, and phase balance. These three parameters cap specific types of electrical pollution. This is the invisible stuff that quietly degrades equipment and wastes valuable transmission capacity if it's left unchecked.
Let's start with power factor. For high-voltage consumers, you absolutely must maintain a power factor floor no lower than 0.85 lagging. If you drop below that floor, you risk needing to install some seriously expensive corrective capacitor banks.
And what's really interesting here is that generators and large solar installations have even tighter specific operating bands. Generators have to maintain 0.95 leading to 0.85 lagging, and massive solar PV systems of 1 megawatt or more, they're squeezed into a 0.9 leading to lagging band just to maintain that overall grid efficiency.
Now let's move on to total harmonic distortion, or THD. This actually follows a descending staircase. It's strictly capped at extra high voltage at just 1.5%, and the limit actually gets looser as the voltage drops, all the way down to 5.0% at low voltage.
Now, that might seem a bit counterintuitive, right? Strictest at the top, but distortion is capped to strictest at extra high voltage for a really good reason. That is exactly where dirty waveforms can propagate the furthest and cause the most widespread damage across the entire grid. Finally, we've got phase imbalance. This measures how evenly the load is spread across all three phases, and it's strictly capped at a maximum negative phase sequence component of exactly 1.0%. So we've fully mapped out the strict limits of steady-state voltage and power quality, but that leaves us with a pretty massive question. What happens to the grid when physical infrastructure suddenly breaks down? Can the network survive a sudden, massive equipment failure without cascading into a total blackout? We'll dive into exactly that next.